we'll now try to develop a mathematical expression to model the stick force. What is this stick force? It is the force applied by the pilot on the stick to deflect the elevator into a particular angle, right? To deflect the elevator to a particular angle. Now, the question is, all the stick force or stick free stability, these have a relevance if I am talking about control system which are reversible. Reversible means, let us understand what is the meaning of reversible. Although I have already explained you in some time, let me draw this diagram. To appreciate the stick force, let us see this simplified diagram. Okay? This is the stick, and through lever you could see if I pull this stick, if I pull it, then this elevator will go up like this. Right? Again, if you see, if I push this stick, push it, then if I am pushing it, then this elevator will go down. So if I pull, you could see that elevator going up, and if I push, the elevator is going down. Clear? And you'll see that as a matter of convention for our lecture, here we have taken pull force to be negative. So let us see what is the meaning of this pull and push in actual flight, which I will be demonstrating you when we will be flying an aircraft. But let us say I am cruising at a particular speed or cruising at a particular CL. Now, suddenly I want to reduce the speed, but at the same time I will try to maintain lift equal to weight. So what will happen? Reduce the speed. The psychologically it is like I am pulling the stick as I am trying to reduce the speed. As I am trying to pull the stick, as I want to try to reduce the speed to maintain lift equal to weight, CL has to increase. So what will happen? As I pull, CL has to increase means the elevator has to go up. You see, if I pull, the elevator goes up like this. As I pull, then this gets stretched like this, and this is stretched like this, and it rotates like this. So that is why when I want to reduce the airplane, I pull the stick, but still I want to maintain lift equal to weight, so my CL should increase, so the elevator will go up, right? In a reversible control, if I have the elevator here, and if I try to pull the elevator up, we'll find the stick will automatically go in a pull force. We'll explain the pull force, it will try to move that side. That is why, and if I want to put the elevator down like this, the stick also will move this way to generate a push force. That is why it is called reversible. That is why it is easy to give feel to the pilot. But in irreversible control, which are most aircraft are, there are boosters, there are actuators, and that sort of a direct reversible relationship is not there. So the stick force relationship will not hold true strictly, and one may ask for what is the relevance also. Okay? But we will do this. We will see that there are important things to learn. So this is what we are talking about. We are talking about a reversible control. And when you are developing a stick force required, we have this diagram or this picture in mind, right? And when we are talking about stick force, we also have relaxed one thing, that now the elevator is no more fixed, right? Elevator is allowed to float. Okay? So we'll revise this. What is this meaning of elevator or float? Already we have discussed something, but we'll further discuss because now we need this background to be reinforced before we write an expression for stick force. Okay? If the elevator is mounted on a hinge, and you all know that, yes, it is indeed. This is the elevator, there is a hinge line, right? And assume that it's a frictionless, then what will happen? See that if there is a positive alpha tail seen by the tail, then there is a pressure distribution over this, and as you know, if the resultant is behind the hinge line, then I get a moment which will try to take the elevator float like this, right? Okay. And nose down, so it is negative in nature, and we said this effect is due to whatever hinge moment is coming is due to alpha tail. Right. But now see also one more thing. If I am trying to deflect the elevator down, okay, so again there will be pressure distribution over it, and there will be a resultant here, and if the hinge line is ahead of this, this also will give a moment which will try to oppose the deflection. Clear? That is, if I am trying to take it down, then it will try to oppose it. If you try to take it up, then again it will try to oppose it. So what is happening? There is a hinge moment generated because of alpha t. As there is a positive alpha t, it will try to float. As it tries to float, now this delta E angle is being introduced. This delta E, because of that, will give a force downward, which will try to oppose it. Right? So we have hinge moment coming not only because of alpha t, but also because of delta E. Is this clear? I repeat again. If this is your elevator, and because of pressure distribution, and if hinge line is ahead of resultant, for a positive alpha, it will try to take the nose of the elevator down, so it will have pitching moment negative. But you also see that if elevator is taken up like this, because it generates elevator angle delta E, and then that will generate a force downward, which will try to take it. For a negative delta E, it will generate a positive pitching moment. Right? Similarly, for a positive delta E, you could see here, positive delta E, the force will be somewhere here. So about the hinge line, it will generate a nose down moment. So what is the message? Message is, with positive alpha t, let's suppose this is the elevator, tail is here. With positive alpha t, it tries to float like this. As it floats like this, because of the elevator angle is changed, it generates a force downward, it tries to discourage it. Right? So there has to be an equilibrium where the net hinge moment because of alpha t and delta E is 0, and that angle we call it floating angle, physically, fundamentally. Okay. So let us try to see a little bit of nature of this hinge moment generated because of alpha t and delta E. Typical variation of hinge moment at alpha equal to 0 for delta E. And I am trying to see what is the hinge moment that is coming nature-wise. We will see that typically the nature will be something like this. This is your for different delta E, of course, alpha equal to 0. So what we are seeing that it is linear to some extent, and at larger delta it becomes little bit of non-linear. What is the meaning we are getting here? At alpha equal to 0, right? We are seeing that or near alpha equal to 0, almost things are linear, and if I write this is hinge moment and delta E, then I know that d hinge moment by d delta E sign is less than 0. Correct? This is the nature of hinge moment generated by elevator deflection at alpha equal to 0, which you can physically see if I am seeing the hinge moment. If I draw it like this, and this is your elevator, I am keeping alpha equal to 0, I am putting elevator deflection positive. The moment I put elevator deflection positive, I know hinge line is here, resultant force is here, which will give me a nose down moment. So indeed the slope should be negative, right? Similarly, if I try to see hinge moment versus alpha at constant delta E, that diagram also looks like this. This is hinge moment and this is alpha for delta equal to 0, let us say. There also you will find to some part it is linear, at higher alpha it tries to become non-linear, not that much, but yes. But for our interest, we will find that the variation of hinge moment with alpha at delta equal to 0, so dHm by d alpha, this is also less than 0, which physically we understand. If this is the elevator, so if there is a positive alpha t, we have seen, the hinge line is here and center pressure is here. This also gives a moment nose down for positive alpha, or you say the hinge moment with alpha, the slope at equilibrium is negative. But at higher alpha it changes, it becomes a little non-linear. But we are more focused here. The catchword is linear, right? We will be exploiting that in expanding this hinge moment at alpha t and delta E. So now let us make an assumption. Let's not forget, we are trying to develop a model for stick force, mathematical model for stick force, and we have kept this schematic at background, where we know the pull force we have taken as negative and push force we have taken as positive. Okay? Let's say assumption, we have seen hinge moment is function of alpha. We have also noted hinge moment is function of delta E, right? And if we assumed them to be linear, the whole variation of hinge moment with alpha E and delta E is linear, then I can write, linear means, please understand, you have been doing it for long. Suppose I want to find out hinge moment at alpha equal to 5 degree and delta E equal to 5 degree. The linearity will help me in expanding this problem as hinge moment, calculate hinge moment at alpha equal to 5 degree, delta equal to 0, then add to it hinge moment at delta equal to 5 degree and alpha equal to 0. That is the beauty of assuming linearity. Okay? It makes life very simple. If this is understood, then you are smart enough, you know whenever there is a assumption that things are linear, then I can write delta Hm, I can write as dHm by d alpha into alpha, or strictly speaking d alpha plus dHm by d delta E into delta delta E, or d delta E is the right word. Mathematicians will not allow me to write so casually. So if that is true, then I can write one thing clearly, that all through my text, when we will be doing the stick force, I will be more focusing, if I know the value of this derivative and this derivative, then I will be able to find out what is the hinge moment coming at a given alpha and delta E through this model. Okay? This is the model we'll be using. It is simply like when you write Cl, Cl equal to Cl alpha into alpha plus Cl delta E into delta E. It is the same linearity concept were also used. I have been repeating it here because once you see hinge moment, then there is every possibility that because of this diagram, you may lose the insight. So again, I want to repeat you that nothing new we are doing. We are still focusing on the assumption that whatever operation we are doing on the linear domain, so you can always use this partial derivative concept. Okay? And because of linearity now also we can write this as any hinge moment at any alpha, I can write as dHm by d alpha. Now I can write alpha, then dHm by d delta E into delta. This is also the beauty of the fact that we are all operating in a linear domain. When I write hinge moment here, I will try to take you back. We were also writing pitching moment, right? But we never worked with pitching moment. We worked with a non-dimensional pitching moment, that is Cm. So here also we will be working with non-dimensional hinge moment. So how do I define that? I define Ch as hinge moment divided by half rho v square into S elevator, C elevator. Remember pitching moment, how Cm we defined? The pitching moment divided by half rho v square S C bar, right? So here we are defining hinge moment, non-dimensional coefficient as hinge moment divided by half rho v square S C C E. And for your information, we already have been told that if this is the hinge line, then C is this from the hinge line, and AC is the elevator area that you know. So using this expression, now I can write CH equal to CH alpha tail into alpha plus CH delta E into delta E. And what is the sign of CH alpha t? You know it is negative. What is sign? CH delta is negative. So I know that if I am having a positive alpha here, because of CH alpha t, the nose will go down, so that it will try to float up like this. And because now it has introduced delta E, this will try to resist. For a negative delta E, it will give a positive hinge moment. That is why CH delta is negative. So there will be a balance between these two moments. One is trying to float, one is trying to bring it back. So there will be an equilibrium, and that equilibrium at which CH is equal to 0 is basically CH alpha t into alpha t plus CH delta E into delta E. And from here, we have calculated delta E float equal to minus CH alpha t by CH delta E into alpha t. Of course, we have assumed that CH not equal to 0. We already know that. So this is the delta E float. Okay. Now there's an interesting thing you should understand. Now let us also carefully see this. We could see that delta E float, it will float up if CH alpha t and CH delta E are less than 0. So this it can float down depending upon the signs also. But mostly you'll find the airplanes are designed such that CH alpha t and CH delta E are less than 0. Now suppose you want that delta E float should be 0. I don't want any delta float. Suppose I want delta E float to be 0. What I have to do? I could see that delta E float will be 0. CH delta E cannot be 0, but it becomes infinite, this derivative. Only way to ensure is that CH alpha t is made 0. That means if CH alpha t is 0, then there is no float. This should be in your mind. You will understand why I am mentioning this thing at this point, right? And how can you make CH alpha t 0? That is, one should have to also give a thought to it. If the hinge line and the resultant of the center of pressure are the same place, same point, then theoretically CH alpha T should become 0. Okay? But there are many other ways to reduce CH alpha T, because we don't want much of a floating tendency of an elevator. We will talk about how it is being done. Okay? But before we go to that, we also should understand this. This is also very important. This gradient, that is d delta E float by d alpha, you could see that is nothing but the ratio of CH alpha T by CH delta E. So this ratio will tell you at what rate the elevator will float per unit deflection or unit alpha tail angle. Okay. This is also a very, very important parameter, design parameter, when you are trying to link all these floating tendencies through a reversible control to the pilot. Right? So these concepts you should keep in the back of your mind. We will be using it as we develop all those forces. Since we are talking about how can you make CH alpha T low so that there is less floating tendency, or CH alpha T theoretically if possible to make it to 0. What is the meaning of CH alpha T 0? Means whatever elevator deflection pilot is giving, right? So it stays there, right? No floating tendency. One of the very popular way of doing it, and this concept is used in trimming the pilot force, how much force you will apply, is through a horn balance. We call it horn balance. It's just a passing remark for you to get a little bit of better feel rather than only getting lost into. Suppose this is the hinge line, okay? And this is the fixed surface, this is the vertical part of vertical stabilizer, and this is the elevator surface, right? It can go up and down, elevator, right? Both sides. Now, naturally, here you will find the CH alpha T is non-zero. It is most probably negative because of this thing, because hinge line will be ahead of the center of pressure over the elevator. If you want to see cross-sectional view, it is something like this, okay? Now, suppose if I do like this, I make the elevator like this. This hole is elevator. Do you see? Now this whole portion moves up and down. So as this portion sees an alpha T, please note down, because of this portion of the elevator, it will try to make, for a positive alpha T, it will try to go float towards negative, float up. But because of alpha T on this surface, it will try to discourage it. It will try to take the nose upward or come to the flight lab. I'll explain you what is it there. We are discussing about floating tendency of elevator. You could see this is Hansa 3 aircraft, and these are the elevator, and this is the hinge line about which the elevator rotates up or down, up or down. Now you see if there is an alpha T, then you could see easily that the center of pressure on this elevator will be somewhere here, and the hinge line is here, so it will have a floating tendency like this. Okay, clear or not? This is clear? Now you see, in normal aircraft, this is only up to this portion will be the elevator, but here, you see this is extension has been put here, and that is part of a horn balance. What happens you see? As alpha T is seen by the tail, this portion will try to float it up, okay, because hinge line is ahead of center of pressure on this surface. However, this frontal surface, you could see this surface, this is here. Here the force will act in this direction, so that will try to give nose up. So what is happening? This portion floating tendency is trying to take it nose down or floating up, and because of this horn balance here is trying to take it nose up or floating down. So it is actually reducing the effect of CH alpha T or reducing the magnitude of CH alpha T. Again, listen, for a positive alpha T, this will try to float it up, but because this portion is there, horn balance, this much portion, here the force will act upward, so it will try to take it down. So effectively CH alpha T is marginalized, it is reduced. So that is one of the advantages of having the is sort of a Horn balance. That is, elevator plus some extra surface which is ahead of leading edge. This surface ahead of leading edge will give a moment opposite to the moment generated by surface behind leading edge. So, if you want CH alpha t to be 0, so ensure that they cancel each other and CH alpha t becomes 0. Okay? This is how we reduce the value of CH alpha t, or that is how we reduce the floating tendency of an elevator through Horn balance. Okay, come to classroom. So, once we have understood this Horn balance, how we summarize, we say because of this portion ahead of the hinge line, it will try to discourage floating tendency by reducing the value of CH alpha t, by reducing this value, right. There are many mechanisms of handling the CH alpha t, but at present we are now going towards some definition, and we will be discussing that, so that once we develop the force expression, all these preliminary concepts are clear. Concepts which are physics based, concepts which are convention based. So, if I now again write delta E equal to delta E naught plus d delta E by dCl trim into CL trim. So, how much delta E required for a particular CL? It comes from the stick fixed stability, longitudinal. We are clear about it because d delta by dCl trim has minus dCm by dCl. So, that minus dCm by dCl is stick fixed case, no issues on that. Now, think of a situation. If delta E float is so happen that delta E float is equal to this value for a particular CL. What is the right hand side? It is the delta E required for a particular CL trim, to trim a particular an aircraft to a particular CL. So, it is basically CL trim. That comes from the longitudinal stick fixed stability. Now, say the way CH alpha, CH delta, etc. has been designed, that we know delta E float equal to minus CH alpha tail by CH delta E into alpha tail, and suppose the way CH alpha t and CH delta E are designed, that delta E float, when I compute through this, that becomes exactly equal to what is the delta E required by itself by floating. That means the stick force applied will be 0, right? You don't require any stick force. So, that is the case where we say stick force is 0 physically. That means if the airplane is designed that whenever it goes to a particular CL, automatically the float is exactly equal to what is the delta required. So, it do not require to apply any stick force, and that is the case in our term through stick force. We say that is a neutral stable case. That is Fs equal to 0. Okay. This here again we are trying to build some convention. Second case we will say if this delta E float is less than delta E naught plus d delta E by dCl trim into CL trim at a given CL. That means what happens? That means, please understand, suppose delta required was 5 degree and by float it has come to 3 degree, that means pilot has to increase the elevator up by 2 degrees. So, how does he do that? He has to put the elevator up, so he has to pull the stick. Okay? So, he has to pull the stick. You could see here he has to put the elevator up, so he has to pull the stick, and pull is negative. So, you could see here if delta E float is less than the delta E required, which is delta equilibrium, delta E trim, then pilot has to pull to increase further angle so that it is equal to this equilibrium and delta required or trim delta required. So we have to apply a pull force. In such cases where you have to apply pull force, we will say this is a stick free stability. As far as stick force is concerned, through stick force is concerned. And obviously, if delta E float is greater than delta E naught plus d delta E by dCl trim into CL trim, that is, whatever delta E has floated, it has exceeded the requirement of delta E through this relationship. As I was giving example, if 5 degree was required, now it has, by floating, it has become 6 degrees. So the pilot has to reduce that elevator, so he has to push it. So he has to push, and this is stick free unstable. Please understand these are part of convention, and this convention has an understanding that from handling qualities point of view, if pilot wants to increase the speed, then he will prefer psychologically to push the stick. So the speed is increasing. If he wants to reduce the speed, he will try to pull it. Okay? From that convention, this, if I translate into FS, I come back to this stick free unstable or stick free stable. This understanding has to be very, very clear before you go for any development of stick force.